University of Queensland. He's a professor of civil engineering at the university, and he's internationally renowned for his work in hydraulics. I think Hubert's interests are primarily in fluid mechanics and hydraulics, largely experimental but also computational. And I think people who are interested in hydraulics probably have come across his textbooks. I understand that he's here as well. So yeah, I'm very happy that Hubert has made all his way from Queensland all the way to Exeter. He's here on a Royal Society International Exchanges Award. He'll be here later after the talk, as well as tomorrow, if anybody is interested in meeting him and exploring further after the talk. So over to you.
Thank you very much, Prakash. Good afternoon, everyone. Thank you for being here. As Prakash mentioned, I come. Just bear with me if I can. Okay. Yep. I'm based in Brisbane, the state capital of Queensland. When we talk about Australia, we need to remember that we are dealing with a continent with very big dimension. North to south, Queensland alone is 2,500 kilometers. Brisbane is also an ideal city to enter Australia for a visit, with the proximity of the Gold Coast and Sunshine Coast, 1 hour drive, and Gary or Fraser Island on Great Barrier Reef, 30 minutes, 60 minutes flight from Brisbane. We are also going to host the Olympic Games and Paralympic Games in 2032, so we hope to see some of you then. And we host also the UQ Hydraulic Laboratory, which is a relatively large hydraulic laboratory. We get 16 flumes from 0.4 to 1 meter wide. We are, I believe, the largest teaching and research laboratory in Australia and likely in Southern Hemisphere. And all these flumes are used for teaching experiments, and we have typically a total of 10 to 12 compulsory laboratory practicals that each of our students are doing during their undergraduate teaching. These facilities are complemented with traditional and more advanced instrumentation, ultra-high-speed video camera, 1 million frames per second, phase detection probe, ADV profiler, but we continue to use a Prandtl pitot tube, a pointer gauge, and a Preston tube. They still have their value for a number of experiments. I joined the University of Queensland 34 years ago. I'm not young anymore. I've been, for all that time, a teaching and research academic. That is like most of you academic, the teacher. I'm doing 40% of teaching, 40% of research, 20% services on administration. My field of interest have been around environmental fluid mechanics and hydraulic engineering. Also, I acknowledge that prior to my academic career, I worked for 6 years in the industry, mostly around fluid mechanics. I've been working in a few topics, and you can see more on that slide. But in the spirit of conciseness, let's go to this talk. So I would like to share with you some thought in relation to fluid mechanics of large hydraulic structure during major flood, with the focus on their hydraulic modeling. And to some extent, this talk could have been entitled "Shaken Not Stirred," because I aim to shake your confidence upon our capabilities to model these monsters. We are going together to try to address 3 key questions. How large the Reynolds number of a hydraulic model need to be to predict accurately the performance and characteristic of a large hydraulic structure during a major flood? Can we trust hydraulic model data collected with Reynolds number between 10 to the 4 to 10 to the 5 to predict the performance of large hydraulic structure? And here the expression hydraulic model refers not only to a physical model, but also a theoretical model or a computational model, with the Reynolds number being the Reynolds number of the validation data set. On third question, are prototype tests conducted for short duration and small discharge genuinely representative and good enough? Interestingly, these questions are not new. They were already discussed 40 years ago at an IHR symposium in Esslingen. And unfortunately, we have not progressed much, as indeed there have been quite a few failures of hydraulic structure science. We may remember the tragic failure of 2 dams in Libya last year, the destruction of a dam in Ukraine last year again, Oroville Dam Spillway, Paradise Dam, and even here in UK, some problem with the Toolbrook Reservoir and Ule Dam or Ballsby dams, which were all near miss. So back to our topic. We are going to talk a lot in the next 30 minutes on the Reynolds number. And I remind everyone that the Reynolds number is a dimensionless ratio of inertial force to viscous force. And today, I will use a definition shown in front of you on the screen here in terms of the cross-sectional average velocity on equivalent pipe diameter. That is the most common definition in the industries. It's the definition used in the Moody diagram. And with that definition, we can distinguish between laminar and turbulent flow on the right-hand side. This is our experiment at the University of Queensland. Within commercial pipes and channels, turbulent flow being observed when the Reynolds number is greater than 10,000, 10 to the 4. And today, I'm going to be blunt. I'm going to talk about turbulent flow only. So, what is a turbulent flow? What type of turbulent flow we can encounter? A very well-known canonical turbulent flow is a developing turbulent boundary layer. Boundary layer, a concept introduced by Ludwig Prandtl in 1904. And a few years later, in parallel with his own former student, Theodor von Karman, Prandtl developed this equation called the momentum integral equation, linking the growth of the boundary layer properties being directly linked to the boundary shear stress, shown here. And if we think of a relatively well-known developing boundary layer, for example, along the wing of an aircraft, and if we use a fighter jet flying at Mach 1.8, the Reynolds number of the boundary layer at the trailing edge is of the order of 10 to the 6. Of course, another canonical turbulent flow is a turbulent pipe flow. Most of you should be, of course, familiar with smooth turbulent pipe flow on this famous equation developed by Ludwig Prandtl based upon the integration of the Navier-Stokes equation using the Prandtl mixing length. Interestingly, this equation, which is the velocity profile in a smooth turbulent pipe flow, was developed by Ludwig Prandtl for the entire cross-section, not just a small region. And his students further contributed to a number of correlations, with on the graph on the far right, the Darcy friction factor as a function of the Reynolds number for smooth pipe flow, with the red symbols being the superpipe dataset collected in North America in the late 1990s, compared with the correlation of Heinrich Blasius, a PhD student of Ludwig Prandtl, on the work of Karman, Nikuradze, and Prandtl himself. Of course, another type of turbulent pipe flow is a fully rough turbulent pipe flow. Prandtl, again, developed an expression for the velocity profile. And his former student, Johann Nikuradze, developed this correlation of the Darcy friction factor for fully rough turbulent flow. Interestingly, correlation that is still valid 191 years later. Looking at commercial pipelines, for example, the Trans-Alaska pipeline carrying crude oil, or the Perth-Calgary pipeline, 600 kilometers long carrying water, at design capacity, that is 100% capacity, they operate with Reynolds number of 10 to the 5 to 4, 10 to the 5. Of course, a third type of canonical turbulent flow is a turbulent free surface flow. And today, I will restrict myself to free surface flow in large hydraulic structure during major floods. These flows are turbulent, implying that when we do some hydraulic modeling, the Reynolds number in the hydraulic model, subscript n, must be also turbulent, must be greater than 10,000. And when we do a combined Froude and Morton similitude, we will end up with a Reynolds number in the model, subscript n, much smaller than the Reynolds number in the prototype, subscript p. And thus, the Reynolds number provides an order of magnitude of the flow because it's proportional to the mass flux. Of course, at this stage, someone could ask me, what about the Weber number? I mean, I talk about Reynolds, Froude, Morton. How about Weber? I could, of course, argue that in a large hydraulic structure, there is no capillary effect. That's true, but that's very simplistic, and it's probably not the right way to teach the topic. There is, in fact, a much better justification, a much more meaningful justification for ignoring, as I do, the Weber number. And that comes to a dimensionless number called the Morton number, named after the lady on the bubble, Rose Catherine Morton, defined as a function of the gravity acceleration, fluid density, fluid viscosity, and surface tension. Why is this important? Why is this number important? Because Professor Helmut Kobust showed about 50 years ago that the Morton number can be expressed as a function of the Weber, Reynolds, and Freud number. And if you remember the Cauchy-Buckingham theorem, also called pi theorem, any dimensionless number can be replaced by a combination of itself and other dimensionless number. Thus, potentially, we could replace the Freud number, or the Reynolds number, or the Weber number by the Morton number. Now, coming back now to the modeling of free surface flow. In free surface flow, gravity effects are always important. So the hydraulic modeling must be performed using a Freud similitude. That is, the Freud number is the same model and prototype. Further, most hydraulics laboratories don't have a lot of money. That's the case at the University of Queensland, that's the case at the University of Exeter. And we will use the same fluids, model and prototype, air and water, implying that the Morton number is going to be a constant between model and prototype. So in turn, the Weber number is no longer an independent parameter, it is a function of the Reynolds number. And when we do a hydraulic modeling of free surface flow, implicitly, nearly everybody is doing a combined Freud and Morton similarity. On the Reynolds number, and more correctly, the differences in Reynolds number between model and prototype will account for potential viscous and capillary effects, while the Weber number becomes totally irrelevant. In turn, the dimensionless flow property are function of the Freud, Reynolds, and Morton number, with Freud and Morton number being constant, and really the parameter that is going to change will be the Reynolds number. So, let us look at the magnitude of the Reynolds number. All of you hopefully should be familiar with this graph. This is the infamous Moody diagram, showing on the vertical axis the dimensionless boundary shear stress averaged along the weighted perimeter. It is also called the Darcy-Weisbach friction factor. The horizontal axis is the Reynolds number, and I remind everyone that all the axes on this graph are in logarithmic scale and are dimensionless. We will ignore the left-hand side of the graph because we are only focusing on turbulent flow. If we are dealing with small hydraulic models, typically with Reynolds number between 10 to the 4 to 10 to the 5, this dashed area will illustrate the range in terms of the Reynolds number, but also in the range of the dimensionless boundary shear stress, with a lower limit corresponding to smooth turbulent flow. And I remind everyone, in particular students, that the flow resistance in Newtonian fluid flow cannot be smaller than that of smooth turbulent flow. Large hydraulic models will operate with Reynolds number between 10 to the 5 to 3, 10 to the 6. And you can see that on this dash area, not only the range of Reynolds number is different, but we start to see some difference in the range of dimensionless boundary shear stress. Small prototype operating at small discharge for short duration, we operate with Reynolds number between 5, 10 to the 5 to 3, 10 to the 7. On large hydraulic structure during major floods, and you will see some photographs shortly, we'll operate with Reynolds number between 10 to the 7, 10 to the 8, 10 to the 9, and potentially more. And to paraphrase the Americans, we have a problem, Houston. We are outside of the boundaries of the Moody diagram, both in terms of the horizontal axis, but in terms of the vertical axis. So much for scaling, so much for modeling. So, let's talk about the key focus of this talk, and the key message I want to share with you. Model prototype compliance for large hydraulic structure during major flood. I call this the inconvenient truth, and you will hear later on what I mean by the inconvenient truth. I remind everyone that compliance means that we follow the same rules. We follow the same rules of similitude, geometric, kinematic, dynamic similarity. We also follow the same basic equation of fluid mechanics, conservation of mass, of momentum, of energy. Compliance might be qualitative or quantitative. I'm always skeptical of qualitative compliance because it's too close to visual illusion, particularly to people who have no experience in prototype hydraulic structure during major floods. And instead, as professional engineers, we should focus on quantitative compliance at the 0th order, within 100%, At the first order, within 10%, at the second order, within 2%. And in hydraulic engineering, we never go behind the second order. Finally, when we talk about compliance, we need to emphasize that the notion of compliance is directly linked to the relevant design parameter. A hydraulic model might be compliant in terms of the discharge capacity and dimensionless discharge coefficient, but might not be compliant in terms of the rate of energy dissipation. So, let us look at a few examples, what I call the bizarre, the strange, the unusual. These two photographs show the bottom outlets of the Three Gorges project in China, photograph that I took in October 2004. The Reynolds number of each bottom outlet is 2.7 10 to the 8. The bottom outlet nozzle is 6 meters by 8 meters, with a discharge velocity of between 30 to 35 meters per second, roughly between 100 to 120 kilometers per hour. I saw this small physical model, 1 in 250 scale at Yichang nearby, and I'm highlighting with the red arrow the bottom outlets, a few millimeters by a few millimeters. Would you trust such a physical model to predict the characteristic of the bottom outlets? Definitely not. It's a no. Another example, this is a Paradise Dam spillway in Queensland, photograph that I took on the 30th December 2010. The discharge at the time was 6,000 cubic meters per second, Reynolds number of roughly 8 10 to the 7, and rate of energy dissipation in the spillway of 2.8 gigawatts. Now, some of you might not understand what it means, 2.8 gigawatt. It's basically as much energy as 3 Hiroshima nuclear bombs exploding every minute. 3 nuclear bombs exploding every minute for a flood that lasted 4 weeks. This physical model at the scale of 1 in 70 was developed with mobile bed downstream of the steering basin to look at the potential scar that could develop downstream of the physical model, or downstream of the steering basin, sorry. As such, for qualitative pattern, this physical model might be okay in terms of sediment transport, possibly to the 0th order. But I will definitely not trust this physical model to predict the rate of energy dissipation on this large dam. This is the Clyde Dam Spillway in New Zealand, South Island, photograph courtesy of Graham Quinn. A key feature of this spillway is the presence of a bottom aeration device about 1/3 down the spillway chute. And at the downstream end of each pier, you might see the intake of the chimneys supplying air to the air slot. The purpose of the air slot is to introduce artificial air downstream of the air slot to prevent or reduce the risk of cavitation damage. Risks that were very high for this project are design flow conditions corresponding to Reynolds number of 3.2 10 to the 8. There were 3 physical studies to investigate the flow property of this dam spillway on its air slot, and my PhD study was in fact the third of that study. I took this photograph myself during my project. You can see on the top left the model of the air slot, and we did some measurement of air concentration and velocity in the jet, and the impact of the jet on downstream. And at the time of this particular photograph, I measured velocity of 18 meters per second at the downstream end. That's roughly about 60 kilometers per hour in a laboratory model. This model certainly gave us very nice result, but it's only a sectional model, 250 millimeters wide. We knew already that we would have some sidewall effect, and we couldn't see the development of transverse turbulent structure. So in my opinion, such a model is not capable to provide us with quantitative compliance right to the second order. This photograph shows the Hinds Dam step spillway in southeast Queensland, 1 hour drive south of Brisbane. Let us focus on this particular flow condition, Reynolds number of 5 10 to the 7, for which the dimensionless ratio of critical depth to vertical step height was 1.6. This number is proportional to a Froude number defined in terms of the vertical step height. So on the next photograph, I'm going to show you an experiment which is in fraud similarity with this photograph. This is a 1 in 15 three-dimensional fraud similar model at the University of Queensland of the Reynolds-number spillway for the same DC overage of 1.6. We use a large model, 1 meter wide enough for a student to go in wetsuit and weather trousers. And we have an intake basin that is 5 meter wide. You can see the kayak here for comparison, with our test section here about 1 meter. That model definitely provides us very nice results. But how can I be confident that we could achieve quantitative compliance right down to the second order? Of course, the next level of Lexus is to do some prototype test. Photograph here provided by Professor Ian Wood, who was the supervisor of this series of prototype tests. He was also my PhD supervisor. And here some tests were done for short duration, a few hours over 2.5 days, with Reynolds number of 9 10 to the 6 and 1.3 10 to the 7. Again, we need to ask the question, this is probably good enough for first order compliance, but how confident are we that we could extrapolate this result to Reynolds number 10 to the 8, 10 to the 9? Who knows? So, the next part is we are going to review some hydraulic structure for which there have been some detailed model prototype comparison with contrasted outcomes. Starting with step spillway on the developing flow region in a step spillway. On the right here, you see the photograph of the Reynolds-number spillway drive. I'm standing here with 3 of my former PhD students, Gong Fu and Sophia, who are still in Brisbane in the industry, Hong, who is at Sichuan University as a professor, and this is Jason and Stuart, our technical staff. A step spillway is basically a steep chute equipped with a staircase invert designed to dissipate some of the energy, and in turn we have a form drag dominated flow resistance, which lead to a highly turbulent flow with turbulent intensity measured in prototype and in the model of the order of 100%. At the upstream end of the flow, we have a non-aerated flow region that we see on the far right in the yellow rectangle. And a key feature of this flow region is a developing boundary layer. The boundary layer grows from the crest downstream. And in that region, velocity measurements were performed at the surface of the flow, with, on this graph, the surface velocity on the horizontal axis, the upstream head on the vertical axis, and basically the flow direction would be from the top to the bottom on the graph. Prototype data are shown in blue and green for Reynolds number of 1.1 10 to the 8 and 4.5 10 to the 7. The red line is the application of the Bernoulli principle to the ideal field flow region, and the black square are laboratory data, 1 in 15 scale 3-dimensional model using Prandtl pitot tube. Now here we have a superb model prototype compliance right down to the Reynolds number of 10 to the 8. So, thumb up in terms of model prototype compliance. Second topic, self-aerated air-water flow. Coming back to a steep chute, and this is the Hubert dam again. On the outer edge of the boundary layer interact with the free surface, we are going to have a mix of air and water called white water or air water flow. And let us focus on this region. Some prototype measurement at the Hubert dam spillway are shown here, with in red the velocity distribution, and the blue asterisk being the air content or void fraction. The larger the void fraction, the more air. So 1 means pure air, 0 means clear water. If we look more specifically now to the distribution of air concentration or void fraction, there we are modeled with an analytical solution of the equation of advective diffusion for air, shown here, and with thick dashed line on the graph. And when we look at it, overall, that's not bad. I would say probably thumb up in terms of model prototype compliance. And this time the model is an analytical model. But there is a term here in this equation which is a dimensionless diffusivity. Let us spend a bit of time on this term. This graph shows a dimensionless diffusivity, vertical axis, as a function of the Reynolds number for a wide range of model and prototype data over more than 5 orders of magnitude of the Reynolds number. The Hubert dam data are somewhere here. And what we see is that irrespective of the air water flow typology, we have a monotonic decay in diffusivity with increasing Reynolds number. Clearly, we have some scale effect. Thumb down in terms of model prototype compliance. Last example, air-regulated siphon spillways. For those who are not familiar, a siphon spillway is a conduit in which the pressure at the highest point will be below atmospheric. They were very common during the late 19th century and early 20th century, and one of their major disadvantages is their startup is brutal. The discharge starts from 0 to maximum capacity in a matter of less than a minute, and it could be very dangerous for people living downstream. So in the first half of the 20th century, there has been the development of this so-called air-regulated siphon spillway to control the release of the flow. This is done typically by inserting a deflector, right here on this photograph, which deflects at the bottom the flow against the opposite wall, with impact on the jet on the opposite wall on a lot of air entrainment in a roller here, which is somehow similar to a roller of a hydraulic jump. And by controlling the amount of air that we provide upstream of the roller, we can control the amount of water discharge from the siphon spillway. But it's extremely complicated. Interestingly, and that's not my work, that's the work of someone else, in particular my late friend Alan Irvine, there had been a superb model prototype comparison published in 1980, comparing 25 years of operation of an air-regulated siphon spillway with a 1 in 5 scale model, as well as a 1 in 10 and 1 in 25 model. And the results are disheartening. There were different head-discharge relationships. There were instabilities in prototype that were not observed in model. There were instabilities in the model that were not observed in prototype. Clearly here, thumb down, there is very poor model prototype compliance. And that's probably why there has been no new development in recent years in air-regulated siphon spillway, to the best of my knowledge. So, we reach the end of this talk, but my conclusion is going to be a little bit lengthy. Let's try to wrap up a little bit where we are at. Large hydraulic structures, during major floods, operate at Reynolds number of 10 to the 7, 10 to the 8, 10 to the 9, potentially more. Plainly, we are dealing with ultra-high Reynolds number, turbulent free surface flow. Let's call a cat a cat. This is not a small Reynolds number. This is ultra-high Reynolds number, turbulent free surface flow. And their modeling is not trivial. I will say their modeling is extremely complicated, particularly because of validation, but I will say also because of a lack of validation data sets. So if I come back to the three challenges, the three questions that I asked you at the beginning, how large Reynolds number of a hydraulic model need to be to characterize accurately the performance of a large hydraulic structure during a major flood? Who knows? The larger, the better. Can we extrapolate hydraulic model data obtained with Reynolds number 10 to the 4 to 10 to the 5 to predict the characteristic of large hydraulic structure? No, definitely no. Our prototype test conducted for short duration and small discharge genuinely representative and good enough? In my opinion, no. So, if I was going to summarize the key takeaways so far, and these are not my last slide because I don't like to finish with negative key takeaways. Model prototype compliance of large hydraulic structure during major flood is very complicated. And bluntly, the inconvenient truth is that there is a very poor model prototype compliance. I hope I've been able to demonstrate clearly to you the relevance and the importance of the Reynolds number in the hydraulic modeling of large hydraulic structure. And we should never forget the magnitude of the rate of energy dissipation during a major flood, which could account for hundreds of thousands of nuclear bombs. But I think there's a ray of hope. My ray of hope is hybrid modeling Mark II. Now, for students, when we talk about hydraulic modeling, we may mean theoretical modeling, for example, using potential flow theory or the method of small squares. We could mean physical modeling using laboratory experiments, and you have some films here in the university. Or we could use numerical modeling, which include CFD modeling and using CFD package. In the last 3 to 4 decades, some people have argued that there is also a form of composite modeling that we call hybrid modeling Mark I, combining physical and computational modeling. Also, many studies that I've seen don't have a great synergy between the two, let's be honest. But all these hydraulic modeling approaches all suffer from validation dataset obtained with small Reynolds number, 10 to the 4 to often no more than 5, 10 to the 5, which in my opinion is not good enough. So I've proposed for a number of years, and I put this black and white 3 years ago, to propose hybrid modeling Mark II combining physical measurement and field measurement using geometric similarity and fraud similar conditions, with an overlap in instrumentation using intrusive and non-intrusive instrumentation. Also, I will acknowledge that one of the challenges is always to get the right flow conditions in the field. Field measurements are never trivial. One example where we've been successful so far has been the Reynolds-number spillway. On your far left, you see the prototype during one of the flood events, and we have analyzed a dozen of flood events over the spillway. And if you look very carefully at the bottom left, you see the contour map of the surface velocity for the photograph shown on the top. The vertical axis is the vertical elevation, the horizontal axis is the transverse location on the spillway, and the color code gives you the range of surface velocity in the depth pin flow region corresponding to the yellow rectangle on the top here. In the middle of the photograph, you see some of the laboratory work that we have been doing, using, for example, some ultra-high-speed video cameras, some intrusive probes with a few results shown here. Now, hopefully, I hope in the last 25 to 30 minutes, I've shown you that water engineering is not a desk job for desk jockey. Thank you very much, and I will leave you with a slide to acknowledge a few people. Thank you.
Do you have any questions? I'll ask one. Yeah. So you showed the slide with the velocities on the top side in the last one.
So on this slide here, the question is related to the bottom left photograph that is seen here that shows surface velocity, contour map of surface velocity on this prototype spillway. This were done using an optical technique, basically using video cameras fixed on a tripod, a study tripod, and we use an optical technique called the optical flow, which is a fairly common algorithm that you can find in various code, which enable us to track basically the displacement of brightness intensity on the movie frame by frame. On this, for completeness and for the benefit for the interest of package, we are looking here at 10 minutes of data.
Sorry, our coffee came late. Please get your coffee, grab your thing. Any questions?
Sorry.
So, what is the solution?
Okay, so the question, I'm repeating the question just for the benefit of what is really the question, the solution. I think the solution, in my opinion, go in two directions. First of all, I think we need field measurements. I've been advocating for the need of field measurement for a long time. It's not easy, it's not simple, it needs dedication, but it is feasible. Okay. I believe, however, that there is some way forward. So I mentioned here hybrid modeling Mark II, so field measurement and field works. I think I could already propose Mark III, field measurements, physical measurement, computational modeling, which will be the way probably to move forward. Also, the investment is fairly massive. I mean, for example, that project on the Reynolds-number took me roughly about 10 years. Also, I was the only one working. I would have loved to have 5 PhD students, 10 postdocs, and a couple of academic colleagues to work with me, and we may have done this probably in 2 or 3 years.
Can you use the imaging, drone imaging?
Okay. So the question is related, how about drone imaging? For the particular data set that I was showing here, drone imaging is not working because it's not stable enough, and the quality of the camera is not good enough. Drone imaging can probably give you some qualitative data, but I would definitely not trust drone imaging to apply that particular technique, optical flow, to obtain surface velocity. Some of the challenges are related to the camera sensor. When you are doing a major flood, it's very often because there are some storms, there is some rain, and the light is usually very poor. So you need to use camera sensors that are of high quality. This here is the type of camera sensor that I'm using. Plainly, it's an SLR camera that costs £1,500. Okay. And I find that GoPro camera, for example, were not sensitive enough for the light change during a rainy period, for example. On a sunny day, perfect. During a rainy period, definitely not.
I may ask something which is perhaps more related to the first part of your talk when you explained some basic principles. A few months ago I had the great pleasure of visiting hydraulic laboratories in Ningbo University and Zhejiang University, where they have 6-7 different models to do with water and air movement in closed conduits. So for example, one thing they are building a lot in China and in Hong Kong, and is a big issue, is those 20, 30, maybe even longer vertical shafts. So would you have any, how to say, general comment or advice which issues should be looked at when we look at not only water but also air movement and effects of air presence in closed conduits?
So as soon as we have air and water present together with turbulent flow, it's very likely that we are going to get some air-water mix, and the water is no longer be a monophase. It's likely to be an air-water mixture. And every time we have two-phase flow, it's extremely complicated, whatever the size of the structure. In addition, closed conduits are probably even more complicated. I'm going to be blunt. In 40 years of work in two-phase flow, I've moved away from closed conduits because it's too difficult. However, I've done some work about 10 years ago on drop shaft. In fact, we have had about a 10 years project on air entraînement in drop shaft. And there, I think there are situations when we can simplify the process. What I mean there is that when you're dealing with closed conduit, air-water flow in closed conduit, generally you are going to have different stages in the flow, which could be very different together. So for example, you will have the shaft itself. Then you will have the impact region. Potentially you may have a deaeration chamber, and possibly you may have a tailwater channel further downstream. If you are able to analyze each of these areas separately, you are going to start to get a better understanding of the key physical characteristics that need to be investigated. For example, if we looked at the impact region, what is going to matter is going to be the impact velocity, the turbulence of the jet at impact, and potentially the aeration of the jet prior to impact. When you are going to look at the deaeration chamber, the inflow condition, and particularly the inflow turbulence, as well as the inflow to phase flow characteristics, are going to be key parameters. If the inflow into the deaeration chamber are not very turbulent, you may have a much better deaeration than if the flow is highly turbulent. If the flow is highly turbulent at the start of the deaeration chamber, you may continue to have re-entrainment of air in the aeration chamber rather than through the aeration process. When you're looking at the tailwater rest channel, on the other hand, it's going to be very much like a spillway chute, where you have progressive deaeration, and depending upon the geometry and the slope, you may have other consideration. For example, if you have a constriction of the tunnel, it might be an issue. That's my thought for now. And I'm not sure whether I truly answer your question.
Well, there is no short and simple answer. I was just looking for some comment. But you're not saying it's complete waste of time. You're just saying it's complicated. Yes?
I'm saying it's complicated and it's not simple.
Yeah.
In my opinion, to try to be blunt, it's not something that can be solved just like this in 1 year project. As I say, I've worked on drop shafts. It took me nearly about 10 years on about 6 different physical studies to start to get a better understanding of the process. And that was just a physical study. I didn't do the CFD. The CFD was done by my friend Fabien Bombardelli at UC Davis. So it's a couple of additional years.
There are 2 questions online. The first one is that experimental measurement or field measurement, which one is more robust to verify numerical models?
Look, if your application is a prototype application, you want prototype measurement to validate your numerical model. If you don't have prototype measurement, you are going to rely either upon theoretical results, for example, potential flow theory, or experimental measurement in laboratory. But at the end, I will always consider that prototype measurement should be your reference. Also, I acknowledge that the accuracy and the amount of data available in prototype might not be as wide or as good as it would be in laboratory.
And the second one from Mark Erich, he said, a very comprehensive lecture. It's French, I cannot speak. Felicitation de Green Hope Hubert. And a provocative question. You haven't mentioned climate change impact on the designing large hydraulic infrastructure. Given your experience, what methodological change you would recommend?
Okay. Look, this whether climate change is of relevance or not is a very interesting question. First of all, I think it's going to depend on which part of the world you are. Okay? In Europe, I know that people are talking a lot about climate change. In Australia, I was attending some keynote lecture just a few months ago, and I participated to discussion on climate variability is a much more important issue than climate change. So, not an easy question altogether. I would like, however, and I'm not sure whether I will be able to do it, would like to mention something else that we need to come back, and you bear with me, it's a slide which is completely at the end, which is not there. When someone starts to talk about what will be the impact of climate change, I mean, potentially, one of the impacts that there would be more hydraulic structure failures. And in fact, I will say, why to date didn't we have more hydraulic failures? I know we had a lot in the last 15 years, but altogether, when we consider the situation, it's not a lot altogether. I'm going to say that we currently rely upon a lot of good luck. Okay? There have been a lot of near miss, Oroville, Paradise, Toddbrook, Goulet, Bulbai, where the spillway failed but the dam didn't fail. Okay? And that's pure plain luck. I think if we think in terms of the opposite, is that on the other hand, there have been a lot of, in the past, design with different approach, different design standard, different design factors. For example, near Brisbane, we have a spillway, a step spillway, it's called the Gold Creek Dam Step Spillway, 1890, still in use 140 years later, built with completely different standard from current RCC dam, for example. I think there's also a difference related to political and economical environment. If we think of some of the hydraulic structure from the late 19th, early 20th century, providing water 24/7, providing resources and water supply to the community was a priority for the government. And the economical interest or economical motivation were not what it is today in 2024. So, if climate change is a challenge, and is likely to be a challenge in terms of hydraulic structure, maybe we need to rethink of the way we approach hydraulic structure not only in terms of their development, their construction, their design, but also their maintenance. Certainly the three test cases that I mentioned in UK are basically simply related to a lack of maintenance of some of their assets. So, yes, it's very interesting. What will be the impact of climate change? I think we need to rethink probably the way we plan to address the long-term operation of some of our structure and assets.
We'll stop here.
Yep.
Thank you. I would like to thank Hubert again for his talk.
Thank you.
Hubert is going to be around